So let's just start. I'm Roger. I work for Citrix on the open source team, and we mainly work on various open source projects. Of course, Zen is the main project that we work on, but then we also have, well, I especially work on FreeBSD, for example. We have people working on QEMU, the Linux kernel. We work on the several components that create the Zen ecosystem, and we only work on open source projects. We don't participate in Zen server development or product or anything like that. So I would like to start with a brief description of a typical Zen system. I have this slide, which is a high-level diagram of a Zen system. On the bottom, you have the hardware. That, well, here I represented the CPU, the memory management unit. Of course, you will also have your these devices, your network, serial, everything. Then on top of on top of the hardware, we have Zen that runs directly on top of the hardware. This is important because it's different from other kind of hypervisors in general. And Zen only takes over the CPU, the memory management unit, and the virtualization extensions. Everything else is passed through to the control domain in order to reuse the drivers that are already implemented inside of guest OSs in general. So when Zen is launched, the first thing that Zen does after setting itself up is to create what we call the control domain. We also call it DOM 0 in general because it's the first domain that's created. So you will see that on some slides or on some papers it's called DOM 0 or control domain respectively. You can choose whatever nomenclature you prefer. And the control domain is a very special domain because it's the first dev that's created by Zen, and it has quite a lot of privileges over Zen. It's able to create other guests. It has access to almost all the physical hardware present on the host. And in general, it can it can do a lot of tasks in Zen. It's in charge of creating the guest that you want to launch afterwards. It's also in charge of migrating them. It's in charge of providing storage for the guest. It's a very special domain. Then on top of this will be the control domain kernel space, and here I have what would be a normal, a control domain user space. In this case, we have syslog, xterm, xorg running inside of the control domain. That will be maybe a normal setup on a desktop Zen host. And then we also have the guests that have been created by the control domain. In this case, I just named them guest 1 and guest 2, but we can have more of them, of course. This is a type 1 hypervisor architecture because, as we can see, Zen is a component that's separated from the guest OS, from the control domain OS. It's not integrated with Zen, and we usually call this kind of design a microkernel hypervisor because the layer that Zen adds is very thin. Zen itself is only 2 megabytes worth of code when compiled and when loaded, so it's a very thin layer. Here on the other hand, I have what would be a type 2 hypervisor. This would be the high-level diagram of any of the type 2 hypervisors like KVM, Beehive, VirtualBox. They all follow the same model. You have the hardware, and then you have the operating system on top of the hardware, and this operating system contains all the instructions and all the knowledge about how to manage the virtualization extension found in processors. And then on top of the type 2 hypervisor or the operating system, you have your task, and these I put the same task, syslog, xterm, xorg, whatever you want to run, and then you have the guests that run on top of the OS. I would like to notice that there are some differences between the different kinds of hypervisors. For example, on a type 1 hypervisor, we can see that the guest and the task that run inside of the operating system compete for resources. On the other hand, on a type 1 hypervisor, the tasks that run inside of the control domain don't compete for CPU time or for memory or for anything with the other guests that are running on top of the hypervisor. And here I have a more detailed architecture of Zen. This is especially focused on the control domain. Like I said, it's a very special domain. It contains quite a lot of Zen-specific code. And here I have the kernel side of the control domain. We can see that we have the paravirtualized frontends, blockfront and netfront. And we also have the paravirtualized backends, blockback and netback. These are used to provide network to other guests that run in the same host. And then I also have a couple of very specific devices. These 3 devices here are exposed to user space and are used by the tool stack and by QEMU or other programs that run in user space in order to interact with Zen. We have the Zen store device. Zenstore is a k-pair value database that's used to share information between guests and between the guest and the host. This is also used to provide the hardware description of paravirtualized devices. We usually refer to this hardware description as the Zen bus in general. And that's how it's called inside of Linux and FreeBSD operating systems in general. We have the Zen bus interface. Then we also have an event channel device. The event channel device is used by the tool stack in order to inject events inside of guests. This is used by QEMU, for example, in order to do virtualization of devices. And it's also exposed to user space. And finally, we have probably the most important device in a Zen control domain, which is the PrivCMD device. The PrivCMD device does two tasks mainly. The first one is it acts as a proxy in order to send hypercodes from user space into Zen. This is very important because all the knowledge about how to create domains, how to build them, how to populate the memory map of domains is inside of the tool stack that runs in user space. But you cannot make hypercodes from user space, so we need this proxy device in order to tunnel the hypercodes from the tool stack into Zen. There's also another very important task that the PrivCMD device performs, which is to allow mapping of memory from other domains. If we go back to the first slide, we can see that control domain is isolated from the rest of the guest. It means that control domain only has a fixed amount of memory that's not shared with the guest. It's control domain memory only. And if you want to access memory from other guests, you need to request them to map this memory into your physical memory map. This is done using the PrivCMD device. This is very important in order to perform things like device emulation, and in general, in order to interact with the guest, you need to be able to map its memory in order to know what's going on inside. And then in the user space size, we can see that we have QEMU. QEMU is used widely on Zen in order to perform virtualization of complex devices. We do some emulation inside of Zen itself, the emulation of performance critical devices like the local APIC, the IO APIC, the PIC timer, the PIC. All these very performance critical components are emulated inside of Zen in order to have very good performance. But then the ATA emulation, the CD-ROM, the emulated network card, all these much more complex devices are not so performance critical, are emulated inside of QEMU. Then we also have Zenstore V that only runs in DOM0. Zenstore V is the program that handles the Zenstore database. This is the main program that contains all the Zenstore database, and it runs in DOM0 user space. And finally, we also have the XL toolstack. The toolstack is used, as I said, to create guests, to manage guests, to destroy them, to migrate them, to save guests. Everything is done using the XL toolstack, which is based on, well, it's POSIX, so it can run basically on any operating system that's Unix-based. And finally, we have Zen Console D, which is a very small daemon that connects to the paravirtualized consoles inside of guest. And then, of course, they also have a couple of VMs on one side. Since Zen was created a very long time ago, when there were no virtualization extensions on x86, they had to come up with a different way to do virtualization in order to obtain very good performance. So they decided that everything that could not be, that need to be emulated, or you need to do binary translation or something like that in order to emulate a fully PC compiler environment, they decided that instead of doing this, you could actually change the interface that you expose to the guest in order to expose something that's much more easy to deal with and that performs much more better. So they created what they call the paravirtualized guest. And as we can see, a paravirtualized guest uses PV interfaces for everything. It has paravirtualized disk, that's block front. It has a paravirtualized network card that we usually call net front. Then it also has paravirtualized interrupts and timers. The way we call the paravirtualized interrupts are event channels, which is a very Zen-specific thing. And the timer is also implemented using what we call the PV timer, which is a shared memory address between Zen and the guest. Then, of course, we have no emulated motherboard on a PV guest. And finally, we also need to use paravirtualized instructions in order to deal with the page tables and with the privileged instructions that the guest wants to execute. This means that when a guest wants to modify its page tables, you need to issue hypercodes into Zen in order to request a modification of the page tables. This is very expensive in general, and that's why this square is marked in orange or yellow in general, because that's something that doesn't perform really good. Each time you want to update the page table, you have to issue an hypercode, which is expensive procedure. So in general, this is the worst point of PV guest. Then in 2004, 2005, when Intel and AMD introduced the hardware virtualization extensions, we started to support what we call HVM guest. HVM guest provides a fully PC compliant environment to a guest, which means that you can run a guest without needing any kind of modifications at all. In this case, if you run a pure HVM guest without any paravirtualized devices at all, you get, of course, an emulated disk and an emulated network card. You also get an emulated local APIC, IO APIC. Everything is emulated in order to provide a fully PC compliant environment. And the nice thing about HVM is that in this case, you can actually make use of a native memory management unit in this case, which is provided by the hardware virtualization extension. This is very important because in this case, the square, as you can see, is marked on green because it means that it needs no Zen interaction at all. It's very fast, and it's provided by the CPU itself. You don't need to tap into Zen in order to modify the page tables. The guest can do more or less everything it wants, and it's very fast. It performs more or less the same as on native. Then we realized that we could also provide TV interfaces to HVM guests in order to speed them up. For example, you can have TV interfaces for disk and net. You can have a netfront and blockfront inside of an HVM guest, and then you will get very good I/O throughput, which is very interesting for us. And finally, we have what we call the TV HVM, which means that apart from using the paravirtualized interfaces for I/O, you can also use the paravirtualized interfaces for interrupts and for timers. This, until 1 year ago, was the guest that performed better than Zen. It had a very good performance because it was using the hardware virtualized extension for more or less everything. And then for I/O, it was using paravirtualized interfaces. So we get a very good performance in general. Then we realized that we may want to create a guest that takes the best of both worlds. As we can see, this one still has a yellow square here, because the main problem with this is that when you want to create a PV HVM guest or an HVM guest in general, you need to run a VM instance in COM0. This is a problem for several reasons. One of them is security. VM has a lot of emulation in it, and of course emulation is hard. There are bugs in emulation, and most of these bugs turn into security issues. This is bad for us. We wanted to get rid of this because most of the Zen security, well, a lot of the Zen security advisories are related to VM, and that's a problem for us. We wanted to get rid of VM. So we thought that we may be able to come up with a new guest type that would take the best of both worlds. This means that it would use paravirtualized interfaces when they perform very good. For example, for I/O or interrupts and timers, you will use the paravirtualized interfaces, but then for memory management, you will use the hardware extensions. We believe that this is the best mode that we can get from Zen and in general from virtualization, which is to use the hardware extensions as much as possible because they perform better. So Oracle started the original PVH work, which at that time they believed that the easiest way to get this was to pick a TV guest and provide it with a virtualized memory management unit. They did that exactly this way. They picked the typical TV guest and added BMX code to it in order to provide a virtualized NMIU to it. So you no longer need to use hypercodes in order to modify the page tables or to execute privileged instructions. This was motivated by two things. The first one was performance. The other one was that the Linux kernel maintainers were really pissed off with all the PV-ops infrastructure inside of the Linux kernel because it was very big and it was very intrusive, because they needed to add hooks to almost all the memory management unit calls. It was something that the Linux maintainers didn't like at all. So they were pushing Oracle quite hard for them to get rid of all these hooks in the generic Linux code. So as I said before, the implementation was fairly straightforward. They decided to put a TV guest inside of an HVM container. They keep the same root protocol. It means that the guest was launched using the same entry point, and more or less the startup CPU state was the same as the classical PV guest, and they removed the usage of all the PV and MIUI protocols in order to deal with space tables. This work was done by Muke Rator from Oracle and George Dalnat from Citrix, and it was merged into Zen more or less 1.5 years ago. After merging it, we realized that there was quite a lot of issues with the approach that they take in order to solve this problem. One of them was that they needed to add quite a lot of TVH-specific code to the Intel VMX code path that are already present inside of Zen. Since they picked the PVGuess and started to use the hardware virtualized extensions, they needed to add quite a lot of code to glue it all together, basically, because PVGuess in the past didn't have access to all these extensions. Then there were also quite a lot of limitations that were acquired from the PV design. The first one, and probably the most important one, was that the PVH-guess could not change phasing modes. This makes no sense if you are in control of your own MMIU. It makes no sense that you cannot change phasing modes. You are in control of it, you can run protected mode, you could even run in real mode if you wanted to. You have your own memory management unit, so you have no problem with it. But due to the fact that it was based on a PV-guess, it was limited. Then there were also other limitations, like the fact that on PV-guess we never provide emulated devices. So for PVH-guess we could not provide a local APIC, an IO APIC, we could not provide any of the emulated devices, and this prevented us from taking advantage of some of the Intel hardware virtualization extensions, like the local APIC emulation, that's now partly done by the hardware itself. And we could never take advantage of this because it was based on PV, so it was very limited. And then there was also another very big limitation, which is the fact that when you launch a PV-guess, you launch it with an initial set of phase tables that are created by the toolstack. This means that when you create the guess, you need to know the bitness of the kernel in order to create the phase tables. This was a very big problem, because now, well, you could not use a bootloader in general, because if you launch a 32-bit bootloader, it means that your kernel must also run in 32-bit. If you launch a 64-bit bootloader, the kernel must also run in 64-bit. This is a very big limitation in general, and we wanted to get rid of all of these. And also the other problem was that support for PVH was limited to Intel hardware with EPP. This is because of the implementation that we did, and since we modified the VMX code path, it was very limited. If we wanted to port this to AMD, we need to modify the AMD code path in order to deal with PVH, and it means adding more code to Zen and making it much more complex, which is not something that we wanted to do. So we decided to go back to the first phase, to the design phase, and let's see what we wanted from a PVH guest and how we could implement it without all these limitations. We wanted the PVH guest to be fast. This means that we need to use the hardware extensions as much as possible in order to improve virtualization speed. We wanted it also to be secure. This means that we will try to limit the number of emulated devices that we expose to the guest as much as possible, and that we, of course, also wanted to get rid of PMO. We don't want to run PMO for a PVH guest because it contains security issues in general. Another point is that we also want to require less modifications to the guest OS. We want to limit the number of lines of Zen code that we need to place inside of guest in order to run in this mode, because we want to have more operating systems that can run as PVH guest. As PV guest, we only have 2 operating systems that supported it. One was Linux, the other one was NetBSD. And it requires a lot of coding that's hard to maintain. We need a lot of people to work on that, and we don't want to do this anymore. And finally, we also wanted a PVH guest to be able to run as .0. If we want a guest to be able to run as .0, we don't need to require a QEMU instance, because we cannot launch QEMU before creating .0. QEMU runs inside of .0, so we don't really need, well, there's no way that we can have QEMU for .0 basically, so we wanted to remove this at all. So to recap, the set of features that we want to do is to use the hardware virtualization extensions as much as possible. We also want to get rid of QEMU, and we want to limit the number of lines of code that we need to add to guest OSs in order to work in this mode. So now a little bit of information about the implementation that we decided to go with. PBGuest only use Zenbus in order to get all the hardware description. On PBGuest there is no ACPI. All the hardware information for PBGuest came from Zenbus. And on the other hand, HVMguest use the Zenbus in order to get the description of PB devices and then the description of emulated devices from ACPI. And on the new implementation, we wanted to do something that was very similar to PBHVM. We want the paravirtualized device information to gain from Zenbus, and we want the emulated or pass-through device information to gain from ACPI. This is important because it means that from Zenbus, we will only get the description of paravirtualized devices, which is easy, is fine. And then the real devices, the physical devices, the emulated devices, we will get the description from ACPI, which is what we do on native. In the past, when you wanted to do pass-through to a PBGuest, you would get the description of the pass-through device using Zenbus, and then you need to hook this into the PCI bus. This is very intrusive, requires quite a lot of modifications to the guest OSs, and we don't want to do this anymore. So we decided that on the new PBH implementation, we also want to provide some emulated devices in order to speed up performance and to limit the number of modifications that we need to do to guest. So we decided that at least we will provide three different kind of environments to HVMguest, PBHV2guest. The first one would be very similar to PBGuest, no emulated devices at all, and all the hardware description comes from Zenbus, because we won't be providing an emulated local API or anything like that, and all the description will be coming from Zenbus. This is a very limited container, and this container won't be able to do PC pass-through at all. Then we also want to provide another mode, which would also won't be capable of doing PC pass-through, but will have a local API. Why do we want to provide the local API to a guest that it's not able to do pass-through at all? We want to do that because Intel and AMD, I think, recently, maybe a year ago or 2 years ago, came up with some hardware extensions in order to speed up the emulation of the local API. So now you don't need to take a VM exit when you access certain local API registers. This is very fast, and it's actually faster than using the TV devices. For example, in this mode, we will be able to take advantage of the local API timer instead of the TV timer because it will be faster. And also in this case, we will be providing some minimal ACPI tables to the guest. The most important one that we will be providing will be the MAVP. This is a table that contains the description of the number of local APIs and IO APIs on the system. So if we want to provide the local API to a guest, we need to provide this table so the guest can find the local API. And finally, the last kind of guest that will be allowed under this mode will be a pass-through capable guest. It will be very similar to the previous one. We will provide the local API for it. But we will also provide an IO API in order to deal with the interrupt from PC devices. In this case, we will be providing more ACPI tables. We will be providing the MAVP, of course, because it contains the description of the local API and the IO APIs on the system. But we will also be providing a DSDT in order to have the hardware description of the pass-through devices. So we also need to change the booting procedure in this case because the PBH booting procedure was not fit for this environment. As I said before, the PBH booting procedure had some initial page tables set up by the tool stack. This is not something that we want to do anymore because we don't care about the fitness of the kernel. We want to be able to run kernels that run in protected mode without paging. We don't care anymore. So we decided to change the interface. Basically now when you load the PBHV2guest, the Zen tool stack looks into this ELF node that contains the entry point into the kernel. And then it jumps into this entry point in protected mode with paging disabled. This means that you can then set up long mode, you can set up protected mode with paging enabled if you want to run in 32-bit mode only. You can do more or less whatever you want. And it is important to note that this is more or less the mode that's used by all the firmware in order to start. Then the segment registers will also be flat. Basically, it will cover the first gigabyte of memory. It will be completely flat segments. And finally, we will place some metadata provided by Zen into the EBIX register. This will contain the command line, it will contain a list of modules that's passed from Zen to the guest in order to boot. It contains also a pointer to the RSVP ACPI table so that you don't need to scan the raw memory in order to find the ACPI tables. In general, we'll try to make it quite easy, and this structure also contains a version field that we may update in the future in order to contain this information if we want to. And finally, it's also important to notice that the IDT, the GDT, or the stack is not set up by the tool stack. The guest has to set up this when booting. An interesting hint is that this boot protocol is very, very similar to the multi-boot 1 protocol, which is implemented by quite a lot of operating systems already. So you could reuse the same, more or less the same entry point without doing much modifications. At the moment, we only support booting PVH guest using the kernel directly, so you mean that you have to specify a kernel in your guest config file. This kernel has to be available in DOM0, so it means that you have to download an image, extract the kernel, place it into DOM0, and then use that kernel in order to boot. We have plans to port at least OBMF, which is a UEFI firmware, so that you can boot into OBMF, and then OBMF will look at your hard drive. You can chain load other loaders in general. We want to make it easy so that you don't have to extract the kernel of your image and boot using that. Now we also have some benchmarks that compare the current implementation with the most performant one that we had before. HVM is the, as I said before, the guest that has the most performance. And I wanted to make sure that the performance on PVH or HVMlite guest was exactly the same or even better as the one in PVHVM, but never worse than it. First, we have a disk IO benchmark. As we can see, the performance is exactly the same as an HVMlite guest, as a PVHVM guest. I also have a network performance benchmark. In this case, we can see that the performance may be slightly better, but there's also quite a lot of deviation here. So I wouldn't like to make assumptions about this. And finally, I have a more CPU-intensive benchmark. In this case, it's the real kernel of the FreeBSD kernel. And we can also see that the performance is exactly the same as PVHVM. So we managed to create an implementation of more or less a PVHVM, well, I guess very similar to PVHVM, but without having PM running in the backend. Now we also want to speak a little bit about the limitations of the classical PV.0, because we want to replace the classical PV.0 with the PVH.0. That's one of the strong points of PVH in general. And one of the main limitations of the PV.0 is that it gets the ACPI tables from the host as they are. This means that there's a lot of information in those ACPI tables that no longer apply, because now you're running inside of a container. For example, the ACPI tables on the MADT, you may see that the host has 20 CPUs, but DOM0 may only have 2 CPUs, because you have limited the number of CPUs that you made available to DOM0. In the past, or for a classical PV.0, you will get all this information and then you will need to filter it out, you will need to add hacks to the ACPI parser. It was something in general very nasty and something that we don't want to do for PVH. There are other limitations of a classical PV.0. All the routing of the physical interrupts and the setup of the physical interrupts on physical devices has to be done using hypercalls, because we don't provide the local API, we don't provide an IO API. So you have to do all the configuration using interrupts. This means that you need to add quite a lot of code to guest OSs in order to support running as DOM0. And finally, as I said, it doesn't have access to a local API or an IO API. We want to solve all this for PVH-V2 or HVMlite. And the first thing that we want to fix is the ACPI tables, of course. So there are two different kinds of tables on ACPI. There are the static tables and there are the dynamic tables that are parsed at runtime by the OS. The static tables are very easy to modify. You can copy them to a different location, you can modify them, and it's not a problem. You only have to recalculate the checksum, which is easy to do in general. But there's a big problem with the dynamic ACPI tables. One problem is because Zen doesn't have any AML parser, so it's not able to see what's inside of those tables at all. So this is a big problem because we cannot parse them, much less modify them, because in order to modify them, you will need to decode the tables, modify them, compile them again, and then place it inside of the guest memory space. This is very bad because in order to do this, you need the full ACPI CA code, which is half the number of lines of all the code inside of Zen. We don't want to import this inside of Zen. Yes?
Have a look at the OpenBSD ACPI implementation.
Not really, but I think, well, you will need a decoder and a compiler. You will need ISL, which is big enough that we don't want to import it inside of Zen. Certainly, I mean, we could do something, we could do some hacks maybe in order to import it, but we have a different solution that I'm going to speak now, which is easier in general, doesn't require importing ISL. So for the dynamic tables, like the DSDT or the SSDT, since we cannot modify them, we are going to use a table that's called STAO in order to add overrides to these dynamic tables. This is a table that has been introduced in ACPI 6.0, and Zen is in control of its specification. It was a table that has been added for hypervisors especially. And on this table, you can actually say which devices are not available to .0. For example, you can say that the serial port is not available to .0 because it's been taken over by Zen. You can say that quite a lot of devices are not available to .0, so it's an easy way to solve this problem without having to modify the DSDT or the SSDT or anything like that. And finally, in order to do interrupt management, we want to do it exactly like it's done on NATE. We want to parse the ACPI tables and we want to interact with an emulated local APIC and an emulated IO APIC in order to set up the interrupts. So we are basically going to provide those two devices to the guest, and then we are going to trap accesses to the MSI and the MSIX regions in order to set up the interrupts on the physical host by Zen, and then to roll that interrupt into the guest. The aim of this is to avoid doing any kind of hypercodes in order to do interrupt setup for .0. And finally, I also have a high-level diagram of what the current Zen implementation inside of FreeBSD looks like. We have a Zen Nexus, which is a specific Nexus that takes care of setting some of the low-level infrastructure for Zen. It sets up the grant table, and it also sets up the it sets up the event channel interface, which is the interface that is in charge of sending and receiving interrupts. And then we have the Zen PV bus, which is the bus where all the paravirtualized devices attached to. We have the grant table code, we have ZenStore, we have the PV timer, the PV console, the PRIV CMD device that we spoke before. We have everything that's contained here, and it only attaches to the Zen PV bus device, which makes it quite easy to work with in general. And finally, I also like to notice that, for example, for .0 or for domains that support ACPI, we will be attaching the native ACPI bus to the Zen Nexus. So the conclusions of all the work that we did in PBHV2 or HVMlite, we have a little bit of a naming problem here, because when we started working on it, we decided to call it HVMlite in order to make a difference with PBH, but then it started to get a little bit messy because people expected PBH, but PBH was never arriving, and now we were speaking out HVMlite, so we had a little bit of naming problem here. But I think we are going to call it PBH at the end, so it's not going to be a difference from a user point of view in general. But the conclusions or the aim of all this work is to make sure that we always try to take advantage of the hardware virtualization features present in the hardware. This is very important for us. We would also like to use the same interfaces in order to provide the hardware description to the guest. It means that if the hardware description usually comes from ACPI, we will provide this interface to the guest in order to avoid us adding new code to the guest. And this brings me to my next point, which is to avoid as much as possible to add code to other OSs, because it means that we have to maintain them, and it takes people to maintain code, and we are not that many people. We want to support as much OSs as possible, so we need to make it easier for people to adapt their own OSs to run as a PBHV to guest. And this means that we need to provide an interface that's quite similar to what's done in native. So thanks for your time. If you have questions, I will also take questions about Zen in general if it's not related to PBH.
Your developed code is still in the base tree and branch?
Yes. For Zen, you mean?
Yeah.
Yeah, well, we already had, when I started working with FreeBSD, there was already quite a lot of Zen code in it. I mainly added the code in order to run as .0. And I I also added a couple more of devices. Well, we've been doing fixes all over. There's also other people from Citrix that contribute to FreeBSD from time to time.
Then all of 4 of these, all of 5 include deviation of the pixel.
Yeah, but it was the old implementation. It was the previous one that we are now trying to override with the new one. But yes, since I think the first one was probably Zen 4.4, which only included PVH support for guest, and then Zen 4.5 was the first one to include Zen support for PVH on 0.
This PVH support
we finished the first, so now let me go back to the slides. Yeah, this is the slides of the different modes that we want to run on. This is now done and it's committed to Zen, so we can run a PVH V2 guest using no emulated devices at all. Now there are prototype patches for this one. So now we are starting to test to provide at least a local API to the guest and to provide some basic ACPI tables to it. The Zen freeze is starting in 2 days, I think, so I'm not really sure if we will be able to manage to get all these inside of the next release, but we release every 6 months, so you don't really need to wait a long time in order for it to appear on the next branch.
Thank you.
I heard that Beehive developer interested in using Vietnam this month to speed up the I/O for network storage. They have the same idea for the development?
Yeah, probably yes. Probably Luigi knows a lot more about NetMap than me. I don't really know a lot, but yeah, we'll try to push NetMap into Zen also, because I think that now if you use Virtual, you can take advantage of NetMap already. It's not something that we have on Zen. We recently have done quite a lot of improvements in the para-virtualized devices, like we added multi-queue to the net from device, and we also added indirect descriptors to the block device, but we still haven't added any NetMap support to Zen both in general. But yeah, it's something that we are looking after. Well, if there are no more questions, thank you for your attention.